Hooke's law is the force law that describes ordinary springs. And to start us off here, I've got a couple pictures of some different types of springs, both of which are at least in part, or maybe in more than one part, governed by Hooke's law. These are some extension type of springs here that can be stretched, or basically tension forces can be applied to them. This is a spring that's actually designed that can be either compressed or stretched. It really doesn't matter though in either case, how the math turns out. The same equation is used for both. It would just have maybe a more limited domain for a spring like this because you can't really compress it. But the basic form of Hooke's law is F is equal to kx. I have here under the key concepts another form, F is equal to k delta L. That's just if you want to use a different variable. I think maybe our textbook uses that one. That might be why I have it there. And some textbooks do use delta L instead of x. I kind of like x because x, I don't know, I think it's simpler. I've also written here a more vector-based kind of form that has a minus sign in it, and it's pretty common to see Hooke's law stated with a minus sign. What that is about is like in this picture here, this is like my basic picture for Hooke's law that relates the force that I use to say stretch a spring, and there's an object here attached to it, but like let's say I grab that object and I'm applying a force to it and thereby stretching the spring by an amount x, then the amount of force I have to apply to give it that stretch x are related to each other by the spring constant k. So this k here that appears in all of these formulas is the spring constant, which is going to be different for every spring. In that sense, k has a different value probably for each of these springs up here or any other spring that you have. And if you ask like, well, like let's say if you could you calculate k for this spring just based on that picture? I don't think I could, to be honest, because I don't think it gives me enough information. It'd be complicated either way, even if I did have detailed information. That's there. I mean, there's some advanced engineering classes I think that cover that a bit more, but we're not going to go there. Anyways, why the minus sign though? Like why is that there? Well, in this picture, something to note is this force F I drew in here, is that really the force of the spring? The answer is no. That's the force that I applied to stretch this spring. Really, the force applied by the spring is kind of back on this. Back on this. Let me switch to the drawing tool I need. Back on this object here. So in other words, and this for that object there is really kind of a force balance situation. I'm trying to get that to look like an F there. But really the force applied to this object to the left there is the spring force. And the thing to notice is that's in the opposite direction of the direction in which the spring was stretched here. So from a vector's point of view, if this F represents the force applied by the spring and this represents the displacement of the spring, this minus sign makes sense in that context. I don't always use that because usually in problems what I like to do is I just use F equals kx, and then I draw a picture, and in my picture, either in the picture itself or maybe with a free body diagram, I make it really clear how things should work with minus signs, and then from there I figure it out as I go into the math.